introduction to your post as Professor of Radioanalytical School of Ocean and Earth Science, and then give us your talk. That'd be amazing. Thank you very much indeed.
Thanks, Julian. Thanks for the invite to talk today, and thanks. It's great to see people online and all the new friends online as well. So it's my great pleasure to be here presenting this afternoon. I'm Professor Andy Cundy. I'm based at the University of Southampton. I've had a long engagement with the Society for Environmental Geochemistry and Health over the years. So I'm a Professor of Environmental Radiochemistry. And I'm based at the Enterprise Unit, GAU, Geoscience Advisory Unit Radioanalytical at the School of Ocean Science down at the National Oceanography Centre, Southampton, University of Southampton's waterfront campus. So when I was asked to give a presentation, I was thinking about what topic to present on. I think last time I presented on the Anthropocene, but really what I wanted to do today was to explore an area where I think scientists and professionals and others who are members of SEGH can kind of make a real contribution to the wider field, and that's around sustainable management of our nuclear waste legacy. So this is an area that I think really could bring together environmental geochemists and also health professionals as well, alongside a range of other professionals in terms of public engagement, geology, geophysics, etc., etc. So I'm going to talk today about sustainable management of our nuclear waste legacy, challenges and opportunities. So by way of a plan, I'll start off by talking a little bit about our nuclear legacy. I'll focus particularly on the situation in the United Kingdom, but also mention some of the international nuclear waste legacy challenges. I'll talk a bit about the key challenges around management of that nuclear waste legacy. And then I'll give some project examples of where we're working at the University of Southampton with partners in the UK and internationally to address some of the management challenges. So I'll talk a little bit about the Surrey project, work using non-thermal or cold plasma, and then work around in situ characterization. And then I'll talk a bit about challenges around achieving sustainable end state. So end state is if you like, the end goal of the cleanup of a nuclear site. So, and how we can achieve that sustainably. And then I'll talk a bit about opportunities, wider opportunities for the SEGH membership to engage in this particular field. And it's certainly, I mean, I'm one of the handling editors on the Environmental Geochemistry and Health journal. And certainly there's been a lot of papers that are submitted and published on, particularly on naturally occurring radioactive materials, but also some on nuclear effluent discharges. So it's an area that the community are already engaging in. So if we look at the UK in terms of the UK's nuclear legacy, we're talking about some fairly big figures, some big volumes and some large costs. Okay, so the 2024 estimate by the National Audit Office in the UK suggested that over 3.3 million meters cubed of radioactive waste currently exists or will be created as our main nuclear waste generator. The Sellafield nuclear facility is decommissioned, basically deconstructed and made safe. So the forecasted cost of decommissioning, just Sellafield, the Sellafield facility, and just as background, the Sellafield facility is where the UK initially produced the plutonium for its nuclear weapons program, but subsequently Sellafield was the site of the first on-grid commercial nuclear power station, power generating facility, and also was the site until recently, until a couple of years ago, where the UK reprocessed its nuclear waste to make new fuel out of it. So that is the main site, the main focus of decommissioning in the UK. There are a number of other sites such as Dounreay, Dungeness, etc. But a cost of £136 billion at 2023-24 prices. And it's estimated that by the Nuclear Decommissioning Authority in the UK, it expects all buildings at Sellafield to be demolished by 2125. So we're looking at a very kind of long-term operation. So Sellafield makes up about almost 76% of the spend, if you like, for management of our nuclear facility legacy within the UK. Other important sites include Dounreay. LLWR stands for the Low Level Waste Repository, where some of our lower activity wastes are disposed to a sealed landfill on the Cumbrian coast in the northwest of England. And there's a small figure at the bottom in the centre there, just to the centre left, 8.3% on the UK's geological disposal facility. So the UK is one of a whole group of nations that are looking at deep geological disposal or subsurface geological disposal for the management or disposal of its higher level waste and intermediate level waste. So the more radioactive components that can't be disposed in the very near surface. So again, the UK, in 2019, the UK's radioactive waste inventory was estimated to be made up of a variety of components. And it's quite instructive to see what those different components are. So nearly 58% of the 5.1 million tonnes total mass of the UK's radioactive waste inventory was made up of cementitious materials. So reactor bioshield concretes, other concretes from around the margins of nuclear facilities, 16.9% metals, 10% brick, stone and rubble, nearly 5% soil, 3.4% other materials, 5.6% organics, and about 1.9% graphite. Now, graphite is quite an interesting management challenge for those nations with nuclear waste disposal issues. And so on the top left of the slide there, apologies for the spelling, it's not actually my diagram, this is from Fu et al. 2022 based on IAEA data. But this is the stockpile of radioactive graphite in tons in various nations. So the main graphite waste holders are the USA, Russia, and the UK. The UK's got the biggest inventory of graphitic waste because we used graphite extensively as a moderator in our nuclear reactors. So we've got an example there of a graphite moderated reactor. That's actually the Hanford B reactor in the US that was used for production of plutonium for the US weapons program. But the graphite is used as a moderator. Effectively, the graphite is used to slow down the neutrons, so they've got more chance of actually interacting with other nuclei and leading to a sustained chain reaction in a nuclear reactor. So in the Magnox reactors in the UK, a lot of graphite was used as a moderator, and that has been activated by the nuclear process, by the nuclear fission process, and that now needs management and disposal. But as well as the kind of power generating side of nuclear, there's also the wider parts of the nuclear fuel cycle. So the image there on the lower right of the slide is entering historic uranium mining area. So this is from the US, and there are a large number of sites globally which have been used for uranium extraction. They need careful management. We have other sites globally as well that have been used for processing of radioactive materials. A number of those on the call will be aware of radium processing facilities where radium and also tritium were used to produce glow-in-the-dark dials on vehicles, and they have led to significant management issues. Most recently, an example of Dalgety Bay in Scotland, where particles of radium-rich materials needed to be cleaned up from the foreshore. And also we have nuclear reactor accidents. Okay, so the top left there shows the aftermath of the Chernobyl disaster. That is the number 4 reactor at Chernobyl in 1986. And also in the lower right there, we have the Fukushima disaster 2011, caused by a tsunami which overwhelmed the Fukushima nuclear power plant and led to significant meltdown basically of the reactors there. And that, of course, released significant amounts of radioactive pollution into the surrounding area, contaminating quite a large areal extent. In the case of Chernobyl in Eastern Europe and the former Soviet Union, and also in the case of Fukushima, large parts of northern Japan. So what are the key management challenges around these nuclear legacy sites? Well, if we think about nuclear facilities, and I include uranium mining sites in that, decommissioning nuclear sites to desired end states. Okay, so I visited this morning actually a nuclear facility in southern England, former nuclear facility, which is undergoing decommissioning. And the idea there is they want to return that site to heathland. Okay, so that is the end state. They want to return it to a semi-natural state. Other sites will be decommissioned to an end state that might be industrial usage. In some cases, for some of the nuclear facilities in the UK, the anticipated end state is released for housing development. So that actually incurs various management challenges. And particularly, there's a key challenge around decommissioning of nuclear sites in terms of reducing the cost. I mentioned the figure of £136 billion for Sellafield, but also the carbon footprint of nuclear site decommissioning. And also, there's a move at many sites towards on-site disposal now. So rather than removing the potentially radioactively contaminated infrastructure to a disposal site, actually looking at dispose in place. So can we make some of these facilities safe in place in the subsurface by capping or other process, and actually manage that risk over the longer term? There's also challenges around permanently and safely disposing of the more radioactive waste produced by nuclear power generation and nuclear accidents. So intermediate level wastes and high level wastes. If we are going to dispose of waste, there's a key challenge around predicting the future for disposal. So if we're going to dispose of nuclear waste, for example, in an underground engineered repository, we need to show that the safety case for that disposal is valid for at least 100,000 years. So we need to predict the future in terms of groundwater changes, sea level changes, climate cycles, etc. There's also a key challenge around public acceptance, for decommissioning, but also for disposal strategies. Can we engage local communities who might regard nuclear activities, radioactivity as being inherently risky? Can we liaise with those public groups to communicate safety cases to allow disposal of our nuclear waste? And on top of that, we've got design for decommissioning of nuclear new build, small modular reactors, and advanced modular reactors. So these are the next generation of nuclear power generating capability. Again, and can we design those and manage those more effectively so we actually reduce the amount of waste and the cost of decommissioning? Can we design them in a modular way so they can be dismantled and decommissioned more easily? And I think in terms of waste management, I'll draw your attention to the diagram there on the right hand side of the slide. Preferred approaches. So this is the waste triangle, or the waste management triangle. So the least preferred option is dispose. And so the idea around nuclear new build is, can we prevent waste being generated as large as possible? If we can't prevent the waste, can we minimize the waste generation and volumes of waste generated? Can we reuse materials on site? Can we recycle to reduce the amount requiring disposal? So I just want to give a couple of examples of projects that we're currently involved in, where we're looking at developing new technologies and risk management methods, mainly for decommissioning former nuclear sites. So one project that's ongoing at the moment is a European Union funded project. It's a twinning project, and it's led by the Technical University of Liberec in the Czech Republic, also involving Southampton, La Sapienza University in Rome, and the University of Granada in Spain. And here we're looking at developing new technologies for risk management and also critical element recovery at legacy mining sites. Now that covers kind of trace element mining sites, but it also covers uranium mining sites. And so there are a number of sites in the Czech Republic, and this is a focus of this particular project, where there are issues around acidic runoff, acidic mine runoff, which the current strategies, as you can see in the top left there, are often liming, neutralization with lime, with calcium hydroxide, and also where we have a large amount of tailings or residues from the mining process that require management. So this particular project is looking at whether we can use electrical techniques, electrochemical or electrokinetic techniques to manage the waste, but also to recover valuable elements from that waste in combination with bioleaching and biorecovery. So the bioleaching and biorecovery is mainly from the University of Granada. And here we're looking at whether we can recover elements from that, critical elements from that waste in usable form. So in bulk form or in nanoparticle form, can we reduce site risk? And can we also recover critical element feedstocks and high value products? So basically recovering value from wastes. So some of the critical elements we've been looking at is arsenic recovery. So basically, can we recover the arsenic in a more stable form and prevent that getting into waste streams? That's from one of the former metal mining sites. But also we're looking at an extensive uranium mining site where uranium is currently recovered, but we're looking at whether other elements can be recovered from that, but also whether we can make the large volume mine tailings present at that site, whether it can reduce the risk of subsurface disposal of those tailings. And that builds on a range of work that we've undertaken over the years, but also are currently undertaking on electrokinetics, electrokinetic remediation for nuclear. So I've liaised with a number of people on this call in previous years on electrokinetic remediation, but effectively what we're doing here is inserting electrodes into a contaminated material, be that a mine tailings or be that a contaminated soil, and using the electrical current to mobilize contaminants and to trap contaminants or recover them. So we've been looking at a number of projects such as the EPSRC Transcend project on recovering elements from nuclear sites or stabilizing groundwater and soils at nuclear sites using these electrokinetic approaches. We've applied techniques in the field. So on the lower right there's an example of an application for plutonium labeled materials at the Atomic Weapons Establishment site in the UK at Aldermaston, where we undertook a large on-site ex situ trial of electrokinetics. And the work on remediation of nuclear sites is being continued by a current Nuclear Decommissioning Authority funded PhD student, Ruby Lunn, there on the lower left, who's working on actually scaling up these techniques for on-site use. So a focus here on low energy electrokinetics using easily manufactured materials. We've also done a significant amount of work on working with colleagues at the Ukrainian National Academy of Sciences based in Kiev. This is a group. We also work with an SME, a small to medium enterprise in the UK, Animad Limited, and they've been working with us on development of low energy or non-thermal plasma technologies. So you can see the low energy non-thermal plasma running on in the pink color on the lower right of the slide there. Cold non-thermal plasma is quite an interesting process because we normally think of plasma as being a form of really high temperature. So you have very high temperatures to form to go beyond a gas and form a plasma. Here, actually, these plasmas can develop at slightly more than room temperature, about 60 degrees centigrade. And they term non-thermal plasmas. So effectively what happens there is the electrons are promoted to that higher energy state, but the ions within the solution aren't. So what we effectively do here is we use an arc discharge and a hydrocavitation process to generate plasma within microbubbles in the treated liquid. So those bubbles collapse, you get cavitation processes, you get hydroxide radical generation, ozone generation. So it's basically an advanced oxidation process. And we've been looking at that for the breakdown of radionuclide organic complexes. So often radionuclides can form highly stable complexes with organic molecules, and that makes it a problem to actually separate them out using techniques such as ion exchange. So it makes them effectively soluble when they would otherwise be able to be absorbed. So here we did some work with the Ukrainian Academy of Sciences and Animad in the Chernobyl exclusion zone. And so the team from Kiev visited the Chernobyl exclusion zone with a modular system for treating liquid waste from the Deprover STO, which is the STO is sanitary treatment object. So interesting site. This is a site that has been open to the elements since 1986. It was used for the storage of solid residues, but also drain water from the Chernobyl 1986 liquidation efforts, the cleanup efforts. So effectively, we have here a liquid rock waste, which has been exposed to the elements. It's had organic materials washed into it over the years. And so a number of the radionuclides in there will be organically complexed. So we use a modular treatment system where effectively we use the cold plasma to break down the organic complexes and then subsequently absorb and remove the radionuclides. So this was an on-site application, obviously in quite a highly radioactively contaminated site, showing, depending on the actual adsorbent you use, more effective removal of cesium-137 in experiment 2, but also strontium-90 in experiment 3. So this is a modular system which can be set up to target the contaminants. You can use different adsorbents depending on which contaminant you want to examine. So obviously cesium-137 and strontium-90 are two medium-lived fission products which are present in the areas surrounding the Chernobyl exclusion zone following the Chernobyl disaster in 1986. So they're about 30-year half-life. So obviously any technique we can use to remove those and concentrate them down into a small residue is very valuable. So here we were able to effectively remove these radionuclides from solution onto a small residue, which then had sufficient activities for it to go to a disposal site, directly to a disposal site. Another area that's we're heavily engaged in with a number of other groups, and it's a real challenge, this one, for the nuclear industry, is on-site rapid screening. And I know I can see Mike Ramsey, Professor Mike Ramsey on the call. Mike's done a lot of work with the nuclear industry on looking at how we can better sample nuclear materials and contaminated soils to actually focus our analytical efforts. And I think this is a really important area that some people often don't realize how important it is. So the importance of on-site screening for particularly DTMRs, these are difficult to measure radionuclides, that's the abbreviation. Basically weak or non-gamma emitting radionuclides. If your radionuclide emits gamma radiation, it's actually relatively easy to measure in most cases, not always, but in most cases, in that you can use an on-site gamma spectrometer, of which there are many on the market, to estimate the radioactive content of a material as you're cleaning a site. With difficult to measure radionuclides, the problem you have is you need to send them off-site for analysis frequently. And so that can cause a delay of 2 to 3 weeks. So if you've got engineers on site and you're looking to clean up an area, if you have to wait 2 to 3 weeks, that adds significantly to cost. So what we've been looking at is whether we can develop readily applicable on-site methods for these difficult to measure radionuclides. So this was work done by a PhD student, Alex Triboulet, who's now at the National Physical Laboratory in the UK. And here we were looking at whether we could effectively develop pH strips, like litmus paper, but use that for radionuclides. So the idea is you have an extractant, which you can either have non-selective or to selectively target a particular radionuclide or group of radionuclides. And then you would put that onto an inert support and use it as a test stick. You would expose it to a liquid or some other material. This can be done robotically. And then you would remove that and measure it on site. So here we tested it for technetium-99, which is a problem fission product on nuclear sites. So equilibration time, 300 minutes here. So obviously for an on-site technique, you'd want less than 300 minutes equilibration time. But here the example was to remove the technetium-99 and then measure it directly using liquid scintillation and other techniques on site. And that really speeds up your what we term post-operational clean-out process and can save the nuclear operator a lot of money. So there is a big emphasis now on in-situ sensing and in-situ techniques that can be applied on a nuclear site during decommissioning, or that can actually be used to monitor deep geological disposal of nuclear wastes. So what I want to move on to briefly now is talking a little bit about some of the challenges around achieving sustainable site end states. So this is adapted from, this part of the presentation is adapted from a special session that a group of us, so Paul Bordos, Eric Milbrecht, Horst Monken-Fernandez and Katrina Turkanu, coordinated at the REMPLEX Global Summit held at the Pacific Northwest National Laboratory, Richland, USA, last November, so November 2023. And this was a special session on ensuring sustainability and resiliency of remediation projects, challenges for long-term management at complex industrial, nuclear, and other sites. And at that particular meeting, we explored some of the challenges which are posed by complex sites, but particularly by nuclear sites. So complex sites are defined as sites with a range of former uses and which have a complex suite of complex mix of residual contaminants, inorganic, organic, and possibly radioactive contaminants. And the alternative definition is a site where remedial or risk management approaches are not anticipated to bring the site to closure or facilitate transitioning to sustainable long-term management within a reasonable time frame. These are sites that require a disproportionate amount of resources for environmental remediation, as well as long time frames to achieve remediation. So remediation or site risk management may involve intensive and large-scale engineering and industrial and stakeholder engagement activities that extend over decades. So complex sites that take a long time to decommission or make safe, for example, nuclear sites. And importantly, as we enter a period of increasing climatic extremes and uncertainties, including major global heating related challenges like flooding, enhanced sea level rise, increased wildfire frequency, and extended drought periods, long-term management and remediation projects need to be future-proofed and resilient. So an example of climate resiliency, this was from a paper we published in 2020. This is an example of Superfund sites in the US, which are located in areas that may be impacted by flooding, storm surge, wildfires, or sea level rise. And that was taken from the US Government Accountability Office in 2019. So the red shaded sites show potentially impacted sites, over half of the Superfund sites. And the bottom graph shows from the top, the percentage of these Superfund sites that are impacted or could be impacted by sea, lake, and overland surges, by hurricanes, slosh. It's a very appropriate definition. Hurricanes of category 4 or 5 and category 1, and those expected to be inundated by a sea level rise of 3, 1, and 0 feet. So basically for the higher category hurricanes, we see up to 12% of sites that could be impacted. And even for the category 1, over 6%. And the sea level rise, obviously the coastal sites, a number of those can be impacted by that. So this is what I mean about needing to build in climate resiliency to risk management and remediation solutions. The other point is around sustainability. There's a need to balance the economic, environmental, and societal impacts, costs, and benefits associated with the remediation of a site and its return to a desired endpoint or alternative use. So this brings in the field of sustainable remediation, which has been really rapidly developing over the past 20 years. And there's a bit of a timeline there in the lower part of the graph. It shows a movement of the contaminated land industry away from kind of dig and dump or dispose to landfill to more treatment-based options, so traditional remediation, through to consideration of green and sustainable remediation. So to remediation that balances the costs and benefits across the social, economic, and environmental sectors, and now move to sustainable, resilient remediation, which incorporates future climatic change. So just as a general definition, sustainable remediation considers the environmental, social, and economic impacts of the project to ensure an optimal outcome while being protective of human and environmental health. Risk management is at the core of that still, both at a local level and for the larger community. And there's an ISO standard on sustainable remediation. So the elimination and or control of unacceptable risks in a safe and timely manner while optimizing the environmental, social, and economic value of the work. And this is really relevant for nuclear sites. But one of the key issues there is how you balance the different dimensions of sustainability and applying or adapting sustainable remediation concepts, practice, tools, and approaches to site rehabilitation or decommissioning. A number of excellent sustainable remediation management systems and approaches have been developed, but how can you apply those at a nuclear sites? Internationally, does sustainability mean the same everywhere? Which tools and approaches should we use? So is it best to use simple, sustainable, or best management practices versus more complex tools? Can these tools support flexible decision-making over long timescales? And can they incorporate changing conditions, including changing climate, but also possible resource scarcity in 20, 30, 50 years' time? And what are the technical capacity needs implement sustainable remediation on nuclear or naturally occurring radioactive mineral sites? Also, can we apply or implement low input remediation strategies? Can we work with nature effectively to realize wider benefits, enhance resilience, and support end state management? So this is an area around nature-based solutions or gentle remediation options. Gentle remediation options are low input remediation strategies such as phytoremediation using plants, bioremediation typically using microbes, or mycoremediation using fungi. These are seen as being less resource intensive, less energy intensive, but potentially can provide wider benefits and also renewable inputs. So can we integrate these kind of nature-based solutions with hard engineering and decommissioning approaches, such as via green cover barriers to stabilize wastes or soil piles or waste disposal areas? You can plant hedges or trees or shrubs as airflow buffers, or intercepting hedgerows for dusts, or as runoff or leachate capturing constructed wetlands or reed beds, etc. So these potentially have lower cost and potentially, and I say potentially, it's not always, enhanced resiliency. They can promote flood control at a site through providing infiltrative surfaces for rainfall. They can provide heating abatement, etc. And we've been doing some work looking at the application of these to nuclear contaminated sites. And so, for example, here we've got the source pathway receptor model in the center of the slide there. So, we can use these gentle remediation options for source and pathway management by greening an area and stabilizing it, by gradually extracting the contamination. We can reduce or eliminate contaminant linkages, and then we can protect the receptor. So we can break that pollutant linkage or contaminant linkage, but we can also provide wider benefits, such as stabilizing within soil, in the example I give here, fission products, reducing the aeolian reworking of contamination, dust, etc., reducing particle runoff, possible integration there with downstream riparian buffers or constructed wetlands. But there's also benefits such as provision of cash crops, material for biomass, bioenergy, etc., enhancement of ecosystem services, and also leisure tourism, physical and mental health benefits for providing areas where people can go into woodland and walk or other leisure activities. And a great example of that is the initiative that's been partly supported by a colleague at University of Portsmouth, Professor Jim Smith, Atomic Spirit. This is the Chernobyl Spirit Company. This is I can't call it a vodka because it's not actually a vodka. It's a spirit which is produced from grain and also from fruit, grown in the Chernobyl exclusion zone. So it's a local cooperative that produced that atomic spirit. I have no declaration of interest there. I'm not on a retainer or any cost share, profit share in this particular atomic vodka or spirit, but it is available and it's used to support local community initiatives. So it's a non-for-profit, so all the profits are ploughed back into supporting the local community in their recovery from the Chernobyl disaster. So with decarbonisation and net zero targets, we can potentially use nature-based solution and gentle remediation options as interim holding strategies to sequester or stabilise contaminated materials, pending final care and maintenance strategies or final site clearance. And potentially they can support transition to green end states. Another key issue is around working with communities to ensure long-term effectiveness, balanced approaches, and also supporting up the spiralling of community capital. So how can we ensure community engagement, particularly at nuclear sites, which have been historically closed or inaccessible for decades? How can we re-engage the local communities? Can we involve marginalised or excluded groups? Including where land ownership, such as around uranium mining sites, but also some nuclear facilities, where ownership and legal liabilities are contested, effectively where Indigenous peoples have been moved off a site to allow the exploitation of the area. How can those marginalised groups, excluded groups, historically excluded groups be engaged? Can we ensure end states which are co-developed to balance social, environmental, economic needs and build on community capital, build on the community skills and interests? Can we assess and quantify sustainability related benefits over longer timescales to inform end states and future site use? So can we capture and quantify some of the value of the wider benefits that might be around transitioning to green end states rather than for built redevelopment? How do we accommodate changing values and desires over time? And how do we build this into end state planning? So there's been a lot of work looking at sustainability linkages in contaminated land remediation. Can we apply that to nuclear sites? Can we transfer that to nuclear sites? And importantly, and key really, can we build future resilience and long-term sustainability into remediation and site end states? Can we cope with climatic shifts and uncertainties and manage impacts on end states? Will intended end states, including green end states, so return maybe the site I saw this morning to heathland, will that still be feasible in 30 years' time under changing climates? What are the possible impacts of changing climate under leave in place in situ disposal strategies on sites? So for example, for leave in place strategies, example there from the EEA of increased fire danger or wildfire risk across Western Europe over the next, I think it's till, for 2 emission scenarios by the late 21st century compared to the period 1981 to 2010. So for a low emission scenario, we still see an increased fire danger risk of maybe 6 to 10%, 11 to 20% or more. Under high emission scenarios, we can see a dramatic increase in fire risk, particularly around some prominent nuclear facility sites, including in France. So that will challenge end state management. An example from the Surrey project, the Czech Republic here, this is the Stras pod Ralskem site. This is a Soviet era in situ acid leaching underground mining site. So effectively here, acids were injected into the subsurface and then pump and treat was used to remove uranium. So this was a Cretaceous sandstone hosted uranium roll-front deposit. And here there were large amounts of acid injected into subsurface, and then that was then pumped out and the uranium recovered. So the area of the leaching field is about 628 hectares. And we can see some huge amounts of acids being injected underground. So over 16,000 tons of uranium via injection of 4.1 million tons of sulfuric acid, 315,000 tons of nitric acid, bit of ammonia, a little bit of added hydrofluoric acid, and 1,400 tons of hydrochloric acid. So that poses a massive remediation challenge. So the challenge here is to protect groundwater, and it's done effectively by pump and treat, coupled with uranium separation and storage or sale. So effectively here you've got a huge chemical engineering plant which is used to neutralize the groundwater and remove the uranium with a target end date of 2037. So the remediation goal, the cost of about €2 billion, is to restore the leaching fields and protect the upper Turonian aquifer, plus sustainably risk manage the treatment residues. So we can see on the top two photographs there, we've got the former injection sites into the subsurface. We have the chemical separation using ion exchange resins to remove the uranium, but also on the lower diagram there, you can actually see the tailings fields. So these are disposed to land and then are capped. But obviously those tailings still contain significant residues, including thoriated materials as well. Now, that particular site is undergoing a pump and treat strategy. So what are the implications of climate change over the treatment period? Well, over the period of that pump and treat strategy and beyond, we're potentially going to see a 25 to 35% increase in heavy rainfall events in this area of the Czech Republic. What are the implications of that for groundwater dynamics? Will that pump and treat scheme still be effective under changing climates? So this is a challenge for that site, and it's a challenge for nuclear sites globally. So, final part of the presentation. The title said opportunities as well as challenges, and I've focused a lot on challenges. But what are the opportunities? Well, I'd argue that these nuclear waste legacy issues are an area, and I know that a number of us are contributing in these areas already, but an area where the wider environmental geochemistry and health community can engage, input, and inform. So effectively, the group online and the wider SEGH community have skills that can really inform decommissioning safety cases, including where material has to be left in place. So the material that's left in place, how will the radionuclides and other contaminants interact with soils and sediments, interact with groundwater? What are the transport mechanisms? Can we improve the predictability of radionuclide behaviour across geological disposal facilities, both in the near field, in the engineered barrier system, but also in the wider geology and subsurface and surface? Can we provide measurement, analytical, and remediation technologies that can benefit the nuclear sector and drive down the cost and increase the sustainability of decommissioning and waste disposal? And also, really importantly, the provision of baseline data. If we are to dispose of waste underground, nuclear waste, then we need to know what the environmental baseline is so we can check for any increase in that environmental baseline related to the waste disposal. So in terms of opportunities, it's an area where we've seen a lot of new facilities investment. So in the UK alone, we've seen a lot of investment over the past 5 to 10 years in laboratory infrastructure by the National Nuclear User Facility that enables academics, scientists, professionals who don't necessarily have radiation handling capabilities in their own institutes to access these facilities and do radiation realistic experiments. So at Southampton, we host the EXACT facility, which is all about next generation characterization or remediation technologies. And we work with a number of partners. They come in and they use our facilities, particularly using radio tracers to test out remediation and characterization technologies. But also, really importantly, there's real opportunity to transfer of skills and methods in from other areas. So, for example, from the ocean sciences, I use that example because it's obviously the focus of the building I'm sitting in currently, the National Oceanography Centre, Southampton. But can we adapt some of the autonomous vehicle technologies and robotics technologies that are currently used at sea to actually, for nuclear waste, such as nuclear fuel storage pond characterization, but implementing skills and methods from soil science, from environmental modeling, and also importantly from environmental health into the understanding of the potential risks around nuclear sites and nuclear site management. And I think the other areas where the community can really contribute is by contributing to scientific and public debates from an informed basis around nuclear waste management and nuclear waste disposal, but also by training a skilled international workforce to deal with these challenges. With apologies to some people on the call, when I was in the US last, they referred to it as the silver tsunami. So the retiring of lots of senior professionals in the nuclear industry and a desire to train up early career researchers who can then come in and help inform and manage some of these major challenges for the nuclear industry as we move forward. An example of that is the Nuclear Waste Services Research Support Office, of which I am the sort of independent radiochemistry lead, which is trying to coordinate a lot of UK activity and international activity in radiochemistry as it informs deep geological disposal of nuclear wastes. So I think it's an area of real opportunity where the SEGH community has a wide range of relevant skills that could be applied in those areas. So I think I've spoken for about 45 minutes. I'd like to give us a bit of time for questions. So I would like to thank you for joining us this afternoon, and I would welcome any questions. Over to you, Gillian.
Andy, thank you very much indeed. That was really, really interesting. I thoroughly enjoyed that. Challenges and opportunities indeed. Can I open this, please, to questions for Andy? If you could stick your hands up on your screen, that would be really helpful to me. Not seeing any coming through just for the moment. So whilst I'm waiting for people, okay, Mike, I can see you've got your physical hand up. Go ahead.
Really good to see you, Andy, and I really enjoyed your talk. Things have moved on a little bit since I did a lot of work at Dounreay, and that was sort of a bit of a pilot project, I think, for Sellafield, and we did lots of that in situ measurement. I'm sure you've read some of it. But one of the things I found, the techniques that had quite a lot of uncertainty, and I was always saying, well, we can deal with uncertainty. We just need to know the cost consequences. And we always used to hit a wall trying to get estimates of, if they get these measurements wrong, how much would it cost them? They just refused to put value on it. So we couldn't calculate optimum uncertainty, for example. So do you think the sector's getting less secretive? They were saying it would affect their share price and one thing and another. So any progress on that front?
It's a really good point, Mike, and I can see the kind of two sides of this. There's two pulls in different directions, because when we had the talk about kind of resilient decommissioning, the comment from the nuclear industry was that we could actually make our decommissioning really, really resilient, but it's going to cost an absolute fortune. And I think that one of the areas that they're really concerned about is long-term liability and consequence costs in terms of reputational damage, because obviously there's a high potential for that. And I think I've seen examples where you think, well, actually that waste material or the waste soil could just be allowed to be disposed in situ, because it's got short-lived activation products in it. If you leave it there for 20 years in a managed way, they'll have decayed away. But often the regulator will say, no, we can't accept that risk, so we have to dispose of it. So you end up having potentially unsustainable practices by digging up waste and creating a hole in the ground and putting them in another hole in the ground, and it drives up costs. So I think there's a desire for a more balanced consideration of uncertainty, and actually developing solutions that, including that uncertainty, but there's still a push to actually, let's just dig it up and put it in a hole in the ground. And I think we are realizing that with a lot of the waste, I mean, the UK's inventory of graphitic waste, you just could not put those in a deep repository. There's not enough room. And so how do we actually more sustainably risk manage that, and how do we include uncertainties when we have material, as you know, that can be very non-homogeneous? So you could have a significant amount of contamination in a small area when you've had a drain leak or something like that, and the meter along you haven't got the same degree of contamination.
Yes, there's lots of work still to be done there, and I'm sure we could talk bilaterally about this at some other point if you want to.
Thank you very much.
Thanks, Mike. Would love to.
Go ahead, please.
No point in me talking to myself. I do enough of that. Yes, very helpful. I've had some dealings with the nuclear industry over time, and I understand some of the issues that Mike's talking about and some of the things you say. I just picked up at the end of your talk, you mentioned about health. I was wondering how the health community could contribute better, or further, perhaps, better is not the right word, further to what's going on. Any thoughts on that at all?
Yeah, I think it's a really good question, Alex, and I think it's almost acting as independent experts, which in the health community used to doing anyway. But I think there is particularly, we've seen examples of this with the UK's geological disposal development. So this is an area where nuclear waste services are, for those who don't know, are liaising with local communities. So it's really unusual in the UK often, and internationally, when there's a national infrastructure project. I hesitate to say for those in the UK HS2, but when there's a national infrastructure project, the government will often say, we're putting it there, this is how we're going to do it. For nuclear waste services and the Deep Geological Repository, it's a community, it's a bottom-up process, it's community-led. And I think there's been examples there, and it's increasingly being realized that we've got very, in terms of the scientific and technical challenges around deep geological disposal, they're quite large, but actually there's a massive issue around societal engagement. And part of that is that, a community would come forward, and members of that community are very concerned, obviously about having nuclear waste as they see under their feet. And I think they would immediately say, well, there's the health impacts. I don't want to get cancer or whatever from nuclear waste, even though the safety case would mean a tiny amount of radioactivity being released over 100,000 years. There's still that perception of a health risk, and I think it's something that Jim Smith flagged very extensively in a talk I saw recently about his work with people who worked on the liquidation, the cleanup around Chernobyl, and they are the ones that are still alive are convinced they're going to get cancer, many of them, and so they're smoking 30 cigarettes a day. So they think, well, I'm going to get cancer anyway, and so it's that perception, and I think this is where health professionals, I think, contribute around relative risks. I don't think we should downplay the risks around nuclear, but it's as we know, you've seen this with potentially toxic elements. It's knowing what those risks are and communicating those risks in relation to other lifestyle risks, etc.
Yes, we in the village I live in Cumbria, in the northwest of England, we're just reworking our village disaster plan for flooding, and mainly for flooding. That's the biggest thing. But the idea of we're over the hill from Sellafield. We're up the stream, up the valley from Barrow, where the nuclear submarines are made. And the issue was raised about putting nuclear risk on the leaflet that we're producing for the houses. My feeling is that we shouldn't, not to deny it, but because it raises unreasonable anxiety.
Yeah.
But it is a discussion we'll need to have in the village. I might come back to you at some point privately on that one, but yes, just use the word radiation or nuclear, and people freeze. Yeah. There's a lot of work to be done on that, an awful lot of work, but there's reason behind it. The industry was very, very secretive for far too long, and government hasn't always helped. And health professionals also haven't helped because they talk gobbledygook for the public. And, and then you go from sieverts to grays to all the other measurements, and I get lost, let alone everybody else. It's a complex area. It's going to take a lot of work.
I agree. I think you're right. I think in many ways that the price is being paid for decades of secrecy, and that kind of lack of trust almost in professionals working in that area.
Oh.
I have a couple of observations and questions myself. If there's, I can't see any other of the yellow hands sticking up on the screen at all. Are there any physical hands want to go up? Oh, okay. I have one. Joshua Abadi, would you like to go ahead with your question, please?
Yeah, hello. Thank you very much for this opportunity. I was just thinking about the question you did ask earlier, and Mr. Alex. I was thinking about the stakeholders' engagement. So I know you did talk about the communities that could be spoken to, the other communities that maybe might not be interested in this. So I was just thinking, does this include like kind of stakeholders engagement? That's my number one question. And the second one was, I was open to hear brownfield redevelopment. I don't know if this is useful from what you earlier said about the old methods, the sites that could be used, and potentially site that could not be used. So I was just thinking if brownfield redevelopment could also be useful for this sort of project. Thank you.
Thanks, Joshua, and great to see you. So yeah, I think the stakeholder engagement is absolutely critical, and I think one of the challenges is reaching all interested parties, and even parties who may not necessarily think they're interested at the moment. And I think particularly in the kind of community engagement, and a number of people on the call have had a lot of experience in this, it's reaching the wider community and not necessarily just the self-appointed community experts or the externally appointed community experts. It's trying to get opinions from the whole community, and I think it does feed in very well to the idea of brownfield regeneration, because I think that is an area, particularly where you've got complex sites, of which we, a number of those are present around the world, the Superfund sites and others, where you need to engage the community over a long period and keep community interest sustained. So I think that's where engagement of the community at an early stage, and particularly where you're regenerating through systems such as gentle remediation options, are really fundamentally important, because you need the local community to actually use the facility and help you maintain that regeneration strategy as well, in terms of helping, using, say, an urban parkland area, using that area, helping you to maintain that area.
Thank you, Joshua.
May
Okay, I will ask mine, and if people don't mind holding.
I have a comment.
Oh yes, go on. Sorry, I haven't seen a hand there. Go on, Olikos, please.
Andy, thank you. It was a very illuminating talk. And regarding secrecy, Alex, I will call it international conspiracy. It's better. You know all about it. Anyway, I'm worried about the injection you have shown us of a lot of acids and afterwards sort of recovering the acids. How safe was this process?
That's a really good question, Alikos, and I think I can be joining those in saying it was completely unsafe. So the injection process was I think we see this quite a lot with nuclear historically. So the priority at that site was to recover uranium to power the Soviet Union's nuclear power stations, and so it was carried out by engineers and site managers who, with the fall of the Soviet Union, returned to their home country and actually left the Czechs with a huge environmental legacy issue. And so, I was, when I saw the statistics for the amount of acid that was injected, it is just, it's staggering. And now they've got this long-term pumping to actually just to try and recover as much of that as possible. But it was a very blunt tool to extract huge amounts of uranium very rapidly, and certainly, effectively these were Cold War drivers that we were seeing, and so you would hope that we've moved beyond that. But I think there are still systems we see internationally where of uranium extraction where again really environmentally devastating techniques are being used, and then people have to come in afterwards and effectively clean up that mess.
Thank you.
That's a really good point to have made. Thank you for that. I've got one or two things. So just yesterday, actually, there was the observation that within Chernobyl they have discovered a virulent fungus which is happily feeding on extremely toxic waste, radioactive waste. Have you come across it? Is it helpful? Is it something that is going to be useful, or is it something that we need to look and go, oh my goodness, we need to keep this thing under control? It's a bit Quatermass again.
I'm pleased you asked about fungus and mushrooms, etc., because I gave a talk and I mentioned a few weeks ago, and I mentioned mycoremediation using fungi to clean up radioactive materials, and I didn't get any other questions. Everyone wanted to know about mushrooms. How do you use mushrooms to clean up waste? And I think I've seen some really good work from the University of Strathclyde in the UK, where effectively they're looking at how you can grow fungi to stabilize contaminated surfaces, contaminated nuclear surfaces. So basically to stabilize contaminated concretes. So effectively these are radiation tolerant species. So I think it's something that we could potentially use, but we need to be careful about using those. Same with any biological treatment. So yeah, promising, but also needs to proceed carefully.
Okay, thank you. That was my first thing. The second thing which I'd noted down for myself was that you commented in there, and if this is just a comment, about making sure that you've got the baseline data. Thank you. I've spent so much time refusing planning permission on things of you haven't got the baseline data. You cannot move until you know what's happening, because how do you know where you're going if you don't know where you've started from? So thank you for that. That's a really good one. Another one was, well, actually it's another one is an observation, which was the silver exit, and getting people trained up, which I think is really, really helpful. So the more people who are engaged on this, and the more people within SEGH in new careers, the better that we have on that.
Exactly. No.
And then just go on. Is that your time up? Are you needing to go somewhere else?
Can you hear an alarm in the background?
Yes.
The fire alarm's just gone off at work, so I'm actually going to have to evacuate the building. I think it's just a test, but my apologies.
No.
It's great to see you all, and all the best for the festive season. Okay, thanks for your
And
attention.
you, Andy, well done.
Thank you
Very
so
good.
much.
I'm off to the assembly point in the car park.
Go.
Bye.
Go.
Merry Christmas to everybody.
And to you,
And you
Alikos.
too.
Happy New Year. Bye-bye.
Bye, people.
Bye.
Thank you for joining
Thank you,
us.
Gillian.
Bye-bye.
Bye.
Bye-bye.
Bye.
Bye-bye.